We can load in the link workspace game onto the root namespace, which gives us the function play. That just gives us a spinning triangle with backface calling. I can look into the namespace state that provides the code for this triangle and spinning, which is APL with SDL3 GPU. We can see that I defined the vertices with APL array notation with the bottom left part of the triangle, the top portion, and the bottom right with the indices 0, 1, 2 for clockwise draw order. I ravel it with the color here using the outer product equals. So if I do the outer product of the indices of 0, 1, 2 and 0, 1, 2, I get the red component, the green component, and the blue component in the identity matrix form. I concatenate that with the vertices to get the actual vertex attributes, which has the positions and the colors for each row, which I ravel to get the actual vertex data, or enlist actually, to get the actual vertex data, which I pass into the transfer buffer alongside the indices, which are drawn. For the view matrix, I do a lookat where I just rotate around the target of 0.5, 0.50, and with the reciprocal of 60 every frame. But let's say instead of a triangle, I wanted to write a quad, and after a quad, I wanted to write a cube. That'd actually be pretty simple. I can just go ahead and comment out the vertices of the triangle, and I can add the vertices of the quad. So 0, 0, 1, 0, 0, 0 for the first bottom left, 0, 1, 0 for the top left, 1, 1, 0 for the top right, and 1, 0, 1, 0, 0 for the bottom right. And for the indices, we have 0, 1, 2 for the top left triangle, and for the bottom right triangle, we can just do 0, 1, 2, 0, 2, 3. So the bottom left part, the top right, and the bottom right. And so we have the vertices, and we have the identity matrix. For the identity matrix, we do commute to do the iota on both sides. We can also add another red component at the bottom, and we can go ahead and replace our color components with that. And if all is done correctly, we should see a quad. There we go. Now, instead of a quad, I want to do a cube. So I'm going to have to move the vertices forward by 1 since this is the front face. And the target, I'm going to have to move the target forward since we're going to be focusing on the center of the cube. So we move the C component forward of the target. And with array notation, I can just make the front face all happen on one line. Which I'm going to comment out as front. And if I hit play, we should see the front face of the cube. And instead of having a mix of colors, right now, instead, I can just have the red component for the front part of the face that I expand by 4, which I can plug in. And if I hit play again, it should pop up, and we get our red quad. And now we focus on the right part of the cube, which is the right components. So we start with the bottom, for the front face, we start with the bottom right point. So it'd be 1, 0, 1. Then we start with the top one right here, 1, 1, 0. 1, 1, 1 actually. Then we move back, so it's 1, 1, 0. And then we go down, which is 1, 0, 0, 0. And so the indices for that are basically the indices for the front cube, but added by 4. So 4, 5, 6, 4, 6, 7, which, since the only difference is 4, we can do an outer product add. Again, 0, 2, 1, 0, 2, 3, which we then enlist to get our indices that we draw with. And if all said and done correctly, we also take the color component and we add green. So 0R, 1G, 0B, And if we do this correctly and we hit play, we should get the right face, which we do. And for the back face, we just take the last two components to the right and then we work with those. So we start with the last one, then we move up, and then we go to the left, so 0, 1, 0, and then we go down 0, 0, 0, which is back. And for the indices and color, it's pretty simple. Since we saw this pattern where we add 0 to 0, 1, 2, 0, 2, 3, we get the front part. We add 4, we get 4, 5, 6, 4, 6, 7. We can just add 8. And we got our vertices. And instead of just manually putting in each number, we can just go ahead and do 3 times, we can get iota 3 times 4, 0, 4, 8, and we can add that, and that gives us our vertices. So we can add that in. And for the color, I'm gonna go ahead and do blue, and if I hit play, we should get the back. Okay. And instead of putting all the color here in one line, we can go ahead and add that as another array outside of the function. And go ahead and comment it. So that we can expand it right here. So now we focus on the left side, just to test that the new color component works. For the left side, we take the 2 here and we go ahead and wrap it around again. Zero, 0, 0, 0, 1, 0, and then we move forward for the left side, so it's 0, 1, 1, and 0, 0, 1. And for the color, let's go ahead and just mix the red and the blue, and we can do an iota 4 instead, and that should automatically work. So now we get the pink. So now for the top, we move from the back and we draw around to get to the front. So 0, 1, 0, 1, 1, 0, 1, 1, 1, and 1 and 0. This is going to be a bit tricky. 0, 1, 0. Oh wait, we already did this here. So 0, 1, 0. We start from the front, then we go to, we start from the front. We start from the back actually. The back left, back right, front right, front left. So 0, 1, 1. And we'll give it a red and a green component. And we'll iota 5 since we're doing 5 faces. And that should work. We now get yellow. For the back, we can just take the top and reverse the order. So 0, 0, and minus the y component by 1. So it's 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0. And we'll go ahead and mix the green and the blue for that this time. And instead of iota 5, it's iota 6. And since we're looking at the top, we can go ahead and look from the bottom. So we set the camera position. Instead of rotating around from the top, we set it rotating around from the bottom looking up. And if we play around, we should see the bottom of the cube. Perfect. And so we have our cube fully completed with the vertices, colors, and indices. Now, I want to make a chunk with that. And I'm going to make it a very simple chunk, so it's going to be 3 by 3 by 3, so 3 by 3 by 3, 0. And I want to have the bottom left back cube and the top front right cube set. So that's just a simple, pretty sure it's a 0, 26, 1, oops, 0, 25, oops. Ah, yes, okay, 0, we take 27 out of 0, and we set the front and the back component, and then we reshape to be 3 by 3 by 3, and that gives us our trunk information, and we can just go ahead and just add that as the chunks. So how do we take this cube and how do we draw a chunk out of that? Well, it's actually pretty simple. We have 27 possible different positions, and for each number, it's 3 different possible positions for each. So we do iota 27, right? We encode that by the length of the chunk, which is 3 by 3 by 3. And each column basically represents a different possible position of a block in the chunk up to the 222 from 0, 0, 0. If we transpose that, we get each possible position as a row. And if we use the rank operator, we can get each row independently and print it out from the defun. We compare that with the vertices of a block, where we select the one row of each possible position, and we select all the block's vertices. State.vertices, not chunk.vertices. And so if we add the second argument towards the print, we get all the possible vertices of a block, and we get the possible vertices of a chunk. So we can do another rank operation to pair each possible position of a block with each possible position of a chunk, and it's going to print a lot. So, but you'll see that it pairs each possible block vertex with each possible position of a block. So if we go ahead and add them together and we check their size, it's 27 blocks, 24 vertices per block, and each vertex having 3 components. We can go ahead and unravel the first 2 dimensions. To get 648 vertices with 3 components for each vertice. And we can go ahead and take this code right here and replace, instead of block vertices, I'm going to name this block V for block vertices, and for vertices, it's going to be vertices doing this, so we can check state block V state vertices, oops, remove the shape, state vertices 648 by 3. And for colors, I'm just going to go ahead and get rid of this. I'm just going to make it all red for now. Instead of indices, we can note that for the vertices, there's 648, and for each quad, we need 6 indices. So we divide by the number of quads, the number of vertices per quad, so 162, which we then iota with, and times by 4, which we plug in for the indices. So this would be 4 times iota 4 divided by the tally of vertices. Rank error, okay. We have to tally that. And so with all of this said and done, instead of doing a color right here, we can do just a red component. With all that said and done, if we hit play, we should get a giant cube, but something is blocking that right now. So state.vertices concatenate with length error. Oh yes, right. We have to expand this by the tally of state vertices. And we also get the red components. So expand this by vertices so that we have 648 color components. And if we hit play now, it's all green. It's all red, I meant. And we can reposition the camera so it's at the center of all the cubes. And we'll just go ahead and make the scope a bit wider. And hit play again. We have a giant red cube that we're looking at. So I can go ahead and modify a bit so we shift how we're looking at. So I'll look away from 7, and I'm rotating around and looking at the cube. Right. So since we have our chunks, we have the chunk data. We only want to render this chunk, this block, and this block. Pretty simple if we enlist it. And since we know each block takes 24 vertices, we expand by 24 and get our size. That's 648. That's the same amount of bit mask numbers as vertex numbers. We can go ahead and filter the amount of vertices by just doing a pretty simple filter 24 by filtering along the major cells with the bit mask generated here. And instead of doing indices based off of all possible blocks, we can go ahead and change this so the index data is the amount of possible chunks, so state.chunks. If we enlist and we sum, we get 2. So we can copy this sort of thing where the indices are actually 4 times iota. So this would give us 0.4. Since we have 2, okay, we actually need to make it 6. So 6 iota 4 times. This gives us the vertices. This gives us the offsets that we need to draw the faces in. So we can plop this in. Outer product add with 0, 1, 2, 0, 2, 3. If all said and done, that should give us the comma right out the namespace. That should give us the 2 cubes we're looking to draw. Perfect, perfect, perfect. I can test by also setting the center one, so 0, 15, 26. That's not the center one. Which one is the center one? Okay. So we have 9 plus, was it 13? I'm just guessing and checking. Okay, we have 3 cubes selected. If I wanted to give each one a unique color, instead of doing a bit mask, I could do a color mask. So let's say 1 equals red, 2 equals blue, and 3 equals, I'll swap 2 with green and 3 with a blue. And let's say we're doing this. We can make a color mask. So the colors are 0, 0, 0 for just nothing. We can ignore 1, 0, 0, 0, 1, 0, 0, 0, 1. And so we can do some interesting properties with like the select and other glyphs where if we have the chunks, instead of doing this where we set 0, 13, 26 to 1, we can set them to 1, 2, 3. So 1, 2, 3, and pop them in. And with these, if I were to enlist this and I were to use these as indices, I can select colors with that, or not. Interesting. I can actually, let's try setting it to X. So X is the block types basically that index into colors. We can do color X, state.color X, and select along the first major cell, and that gives us the colors, which we expand by the amount of vertices to 24, which is 648 by 3. And so we can test that. I'm just going to go ahead and add CI for color index. And I'll set color index to be chunks, raveled. Oh, we don't even need to do this. We can just do color chunks alongside the major cell, expanded by 24, and we concatenate with that. We concatenate the colors with that. So right here, we concatenate both, and that gives us the information we need. And instead of using the chunks as a mask like we do here, we'll make another variable called solid, which is utilizing APL's rank polymorphism. We can just do chunks is not equal to 0, just to indicate whether or not there's an actual block there. We can test right here. And it lists any blocks that aren't as 0 as 1, which is pretty cool. So we can filter out, we can replace chunks with solid right here, solid, solid, and if all said and done, this should give us colors. There we go. Perfect. Now we can get a bit crazy with this and do some interesting stuff, because I also have a namespace called Mario, which has colors and data of the NES Mario sprite, where we have, you can vaguely see we have like the hat, the body, and whatnot, and they correspond to the NES colors. And I can go ahead and just plop this right here. So we have our data, we have our colors, and we want to, I'm just going to name this Mario data and Mario colors. And we want to display that to view in 3D. And so I can work on that. So for the Mario size, state, Mario data, state.Mario data. We have this information. We can get the size, which is 17 by 12. I would like the x-axis to be 17, the y-axis to be 12, and the z-axis to be 1. So the chunk size would be 17, 21, 1, 17, 12, 1. That we select, that we first select out of 0. That we then put the Mario sprite into. So chunks, instead of all this, we'll have a chunk length of 17, 12, 1, 0. And instead of doing 27, we can just do a times sum reduce of L, which is of the shape of L, which gives us the amount of blocks, which is 204, which we then reshape for as L. All right. So our vertices, we'll move these to the front. And we can do, we'll move L before the vertices and indices. And we can just go ahead and do L, shape of L, we can do L times reduce, and this will just be L, we get an index error complaining about the size of it right now. It should be able to run fine. We still have the cubes. Since everything is happening on the X and Y plane, we can see we still have the cubes moving up like this. And since we have the chunks right here, it's a matter of getting the Mario data onto the chunks. And since it's reverse, we need to flip the Mario data. It's reversed. The 0 starts here and the 16 is over here. We need to flip the Mario data over for it to be viewable properly. So we have the state Mario data, and if we flip it, we have this. And we need to find a way to set the actual chunks to have the Mario data on it. So it's chunks. This should be doable. And we can just set upside down just to not worry about it. And if we go ahead and play, oh, interesting, interesting. And if we go and zoom out, so for the target, it would be state.l divided by 2. If we hit play, oh, interesting, interesting. We're getting there. And if we zoom out a bit more, where we have and instead of rotating the camera around and trying to figure out how that works, we can instead look from here, play, and we get a very interesting looking Mario. And instead of the colors right here, we do the Mario colors. So we replace the color Mario colors. We get the NES Mario. It's kind of rotated around on the front like that, so we just flip this and that around. And I think that to solve that around, we just transpose the Mario. And if we play, it's flipped upside down. We can flip it around. Oh, other way around. We get Mario. NES Mario with Mario colors. And that's pretty cool. That to be able to get the Mario appearing in APL like that took around this data, the block data, length, modification of vertices and indices to work like this, chunks that we can fix just to we can view like this, and slight modifications of how we do the geometry like this. All very neat. I hope you found this very interesting, and thanks for watching to the end.